Hmm. Hi, Professor. Good morning. So I'm Bhuvanendra, uh, your student of probability class. So I'm going to explain my final project, which is I took a data set from Kaggle. It's a well-known data science community online. So my theme of the project is analyzing the medical expenses of people in the US. So I got this data set. Let me break the screen. Yeah. So I got this data set from Kaggle. So let me just go to that website and explain in brief. So it's a simple data set, but it's so generally, my aim is to finally predict the predicted expenses of a particular person. If given the scenario, we have the details of his biodata, like his income, his age, if he has children, what are the how many are there, and uh, like what's his height, weight, body mass index, especially the one, and his gender. And yeah, we found a lot of shocking patterns in which is related to sex as well. So we'll discuss them. So this is the basic overview of the data. So the columns that we have are age, uh, what's his gender, BM, body mass index, yeah, whether he smokes or not, he or she. So I mean, smoking is injurious to health. So and yeah, the region as well, which region he belongs to. Like since the data set is belonged to United States, whether he's from the north part, south part, east or west. So it's not specific to state, but yeah, from where, which region he came is there. So that's the overview. Let's just go to the my code and let's get started. So I'll just go directly to the PDF that I have got from RMD file. So yeah, initially the basic steps, like I set my directory to probability doc file that I have on my desktop, and I set the seed. It's generally to you know eliminate the randomness. Whenever we run the data, it doesn't, like, since it involves machine learning, right? When I resample the data in the further steps, it divides randomly the data of 80%, 20%, whatever the percentage that I give. So every time when I run it, it should not take some other random like data points. So I will get all the time the different results. That should not happen, right? So I generally give some number. We can give anything. So based on this, I can eliminate the randomness, and whenever I load it or run it, it will get the same results unless and until I change the input. So I'm just reading the data set. So these are the starting five rows of the data. It involves the age, sex, BM, body mass index, number of children. So it's a clean data set. It doesn't have any outliers, or sorry, it doesn't have any null values or missing values. So uh, because our main goal is to use the you know methods that are used in our textbook, like doing hypothesis test, visualization, and fitting linear regression, cross validation, ANOVA test, and all. So that's what my theme is to do. So that's why I took a simple data set which doesn't have any null values. So the dimensions are around, I have 1300, 38 rows that are data points and 7 columns, which are the ones that are above. And charges is the dependent target variable that I'm going to predict, right? That's the medical expenses of a particular person based on these features that are available: age, sex, BMI, smoker or not. So here I use the structure of DF, the data frame gives us the basic input of what is the data type the each column is stored. If it's int character, means like sex, it's a string, so it's stored in that, and we have to change this data types into factors so that we can use machine learning, because all machine learning algorithms doesn't read string characters. We either have to change them into factors or binary if they are two categories like male and female, using some methods like one hot encoding or something in Python. So in this, I have used to as factor function to change every string one to factor. So this is the summary of, like, if the age column, what is the minimum age that is present in the entire data set? That's 18 years. There is a person with 18 years, and the maximum is 64 years old guy. And on our and many most frequent people are at the age of like 39, 40 ish. And so yeah, and number of children. There is a person with five children, and there is a person with one children as well. One child, sorry, without a child as well. So that's that's related to children. And yeah, so coming to medical expenses, there is a person with 63,000 US dollars per year expenses that are given to medical, like under medical expenses. That's a lot. So we will analyze like what's the proportion, or is it an outlier that indicating that much difference, because the minimum charge is 1100 and the maximum is that 63,000, right? That's a lot different. There's a lot of difference. So yeah, coming to here, I'm checking the null values. As I said, I prefer to take an data set which is already clean, so I don't have to go through the process of data cleaning and all. And yeah, these are the basic packages that I have, loaded. Dplyr, tidyverse, magic tricks. These are the packages that I used later on. So to resampling and all. And ggplot is to use plotting, like in like in Python we have matplotlib, seaborn, right? Similar to that. And there is this caret package which I use for the machine learning part. I use create partition and all. For that I imported them. So starting with the first step, exploratory data analysis. This step contains, I forgot to mention here, the fifth chapter. There are a couple of topics that are involved in fifth chapter as well. So it includes everything related to 5, 6, 7, 8 until visualization topic in our textbook. And 11, 12 parts are really involved with hypothesis test and machine learning, which are coming on the next step. But exploratory data analysis, I specifically took time to do some visualizations specific to each feature, and got to know the data much better. So as I said, so yeah, the first step is to finding any duplicates are there or not. I mean, because having duplicates doesn't make any sense. It's just a waste of storage, and the model becomes much complex. So I found out there is one duplicated column, and I just duplicated data is unnecessary to have, so I just dropped it. Then yeah, as I mentioned before, we should not have any column with string storage, string data type, or so that I have like to do even any analysis. Having string data type doesn't help us. So I converted into factors since they are categorical data. So as factor is a function, inbuilt function, which can be used to convert them as a factor. So here you can again see calling the structure of df. I can see there are two levels in sex, which is one is male and one is female. One represents male, sorry, one represents female and two represents male. That's the level. And children, number of children, sorry, what is, yeah, smoker. It is also two levels, because yes or no, it's a binary factor. Two means he or she doesn't have a smoking habit, and yes means one. And the region, yeah, this is one more string stored, and now it converted into factor. There are four levels. That means basically there are four categories in the region, which is northeast, northwest, and southeast, southwest, if I'm not wrong. So we'll see later. So according to that, the numbers are given 1, 2, 3, 4. And starting with each column, basically I just want to get to know the each feature. So in children, there are around 573 people without any child. and there are 18 people with 5 children in their family. So most of the people doesn't have a child in our data set. So that's a thing to note. And yeah, some points to note from summary of DF which we saw in earlier here on the bottom, is that uh, in sex column, male and female are almost equally divided, right? This is an important thing because let's say there are out of 1,000 people that we are going to analyze the data, let's say only 100 people are female and 900 people are male. And later on, when we split the data into train and test, and there is a possibility that the entire test train data only has male points, right? Because 900 of the 1,000 points are belong to male. And when while we are testing, if let's say there is a point with female, and the model doesn't know what to do, right? Because it never learned there is another person called as female, right? So we always have to make sure these are there. I mean, if let's say our data set is not balanced, we have to do something to make it and the model understand that uh, there is another category called as female exists. But here, luckily, we our data set consists of male and female, which are almost equally divided. And see, here we can see, as I'm mentioning before, smoker column. There are almost 1,000 people without a smoking habit, and 274 people with smoking habit, right? That means, let's say, I mean, talking about the data, most people doesn't have a smoking habit. Then we can think most people might also have less medical expenses that we will analyze later. And yeah, here, as I said, in region column there are four categories, right? Northeast, northwest, southeast, and southwest. Here also almost all the people are equally divided within all four regions. And yeah, so the point already I discussed, the minimum medical expense is 11,000 and the maximum is 63,000. Yeah, as I mentioned, it might be the reason 63,000% might be an outlier, right? So we're gonna analyze about that. These are basic things that I want to check whether having more number of children makes a person have more medical expenses. It is a valid point to think, right? So I just filtered using the filter function from our textbook itself, from chapter 6, if I'm not wrong. I try to filter out based on number of children, that's medical expenses, so that we can understand something. So here you can see there is a female person, let's say here on the fourth column, 48 years old female. Um, she has 4 children. She don't have a smoking habit. She came from Northeast region, and her medical expenses are like 11,000, right? That's not too much, and she has 4 children. So this might make us think having more number of children doesn't mean you will have more medical expenses. So we can't just tell from one point. We'll get to know them from some visualizations, but it's just a discussion. So yeah, here again, I just want to filter out using filter function. If there is a person with smoking habit and age is more than 60, right? It's obvious that I mean, a person with much older person might have a lot of medical issues. Plus, he or she has more medical expenses, and if on top of that, if he or she has a smoking habit, that obviously leads to much more health problems. So obviously what I thought became true, like, see, every person almost 30,000, 40,000 US dollars, even though they don't have any children, just because they have a smoking habit. And most of them are like their age is like more than 60 years, as I filtered out. Their expenses are more than 30,000, right? So again, here again, I contradictory check whether if they are more than 60 years old and don't have a smoking habit, then what's their charge? Medical expenses. See, 10,000, 11,000, 15,000. Almost every person has less than 15,000. You can see. So That means smoking is an important factor that's deciding the medical expenses at the end, right? So that's one point we can note. And again, filter function can be used for many every almost every numerical feature. So again, I filtered out using body mass index greater than 45. It's mixed, right? There is a person with 8,000 and there is also a person with 63,000. See, here we got the person who has the most expenses. She's a female, 54 years old. Her body mass index is 47, which means she's obese. I mean, that means like her health is not so good. She's fat and not so tall, I guess. And she has no children. She has a smoking habit and she belongs to Southeast region, and her expenses are the most like 63,000. That's a lot. So and now instead of like filtering out each column, I just filtered out directly from the target variable charge medical expenses greater than 45,000. So let's say if a person has more than 45,000 medical expenses, what are their features, what's their age, what's their sex, what's their BMI, what's the smoking habit they have, right? So you can see a lot of people are I mean almost all people have smoking habit. If they I mean if a person has more than 45,000, let me put it this way: if a person has medical expenses more than 45,000, it means he or she has a smoking habit. You can see every person has there are 38 people out of all 1,300 whose medical expenses are more than 45,000 US dollars, and everyone has a smoking habit. That's an important thing, right? Like if you have smoking habit, obviously you will have more medical expenses. So these are the few points that I wrote down here just so I do not forget. And yeah, uh, World Health Organization (BM) said that body mass index greater than 35 is considered as extremely obese. So that's not very good for health. And here we can see, again going back to the slide, if a person has more than 45,000 US dollars of medical expenses, let's check their body mass index. Everyone almost have more than around 30 35, more than 35 of their body mass index. So we can think it on the other way as well, right? Like if their health is not good, it might be the reason they're like their body mass index is extremely obese. They're not taking care of their health. That might cause them a lot of health issues, and on top of that they are smokers. So we can know we can understand why their you know expenses are so high. And then yeah, there is another function in our textbook, group by. I have used this as well, like mixing two functions. It's an aggregate function summarize inside a sum. Like I'm summing up all the medical expenses by grouping a particular region. So we have three categorical columns, if I'm not wrong, which are sex, either male or female, and then region, whether they are belong to which region, northeast, northwest, southeast, southwest. And then the third one is what's their smoking habit. Do they have smoking habit? They don't have smoking habit, right? It's a so these are, and we can use group by only on a categorical column, right? We can't just use on every column. It doesn't make a grouping function. So I grouped on a region column, which got as a result uh, like you can see southeast, people belong to southeast have more medical expenses. And point to remember, yeah, I got here only. Yeah. So before we got to know that all regions are almost equally distributed, right? So if they are almost equally distributed and southeast people have more medical expenses, that means why, like what is the reason the people belong to southeast have more medical expenses? And that is one more point that I have tried to analyze. So coming to visualizations that we have, like uh, and up until now the data analysis that we have done on each column, I've tried to visualize and better interpret the data using a couple of plots like bar plot, scatter plot, box plot. I mixed a lot using the visualization a part in our textbook. I think it's, let me check. I think it's, yeah, chapter 7. So how you, I think I did around 15 plots. So the first one is distribution of age, right? We need to know like what I mean, what at what group of people are more belong in our data set. Like, so we can see in 20s there are many people, like almost 250 people out of 1300 are in their 20s, and it's almost again more people are in 40s and 50s. So this is a bar plot, sorry, histogram, sorry. And the second plot is distribution of people from different regions. As I said before, almost all four region people are equally distributed among themselves. And here the aggregate function I used is count, because I have to count the number of people from each region, right? It's like a group by function, right? So the third plot is distribution of sex, the male and female, and again, as we mentioned before, they are almost equally distributed. Yeah, and coming to another histogram, distribution of medical expenses. This is our categorical variable, and now we can clearly understand what portion of our people have what range of expenses, right? So almost I can say 50%, almost 50% of the more than 50% of people have their medical expenses less than 20,000, right? So it's right, it's skewed right side. So most people are in the left side. And yeah, so before I already said we will analyze later on whether the 63,000 medical expenses person is an outlier or not, right? So we can see from box plot that I have done here, there are like 1, 2, 3, 4, 5, 6, 7 people which who have their medical expenses more than 50,000, right? Just 7 people out of all 1,300 people. So they're obviously outliers. And so I mean, we need to take care of outliers, right? Because they can mislead our final output and interpret our data, like interpret our results. I mean, so when we draw a medium line, let's say statistically speaking, when we draw a median line, right? Because the values of these are more, just five values can shift our median from 20,000 to 30,000, right? So, like, giving importance to just 5 or 6 people out of all 1,000 people doesn't make any sense. We should take care of these outliers so that our end result will be non-skewed or non-biased, right? There is a topic bias variant instead of that we have analyzed later on. So there we took care of these outliers. And the sixth plot is uh yeah, how many outliers are there, right? I'm just telling before the code comes. So yeah, so these are the outliers, almost 113, 7, 8, 9, 139 values are outliers. These are the outliers that the box plot by default predicted. And we can do customization, we can change the percentages of the outliers. So that's what I did here. Let's say what I filtered out is the least 5% of the data of the medical expenses, and the highest 5% of the uh, medical expenses are outliers, and the middle 90% is our main data to focus, right? So I have like, so that gave us the least fifth percent person has an expense of $1,700 just in a year, like just $1,700 in an entire year. That's very less. And the 95th percentile person has an expense of 40,000, around 40,000. So that means like 90% of the people have their expenses in between like 2,000 to 40,000. So this is where we have to concentrate and interpret our results at the end. So I have removed those outliers to just so yeah. So these are the removed values, and the end uh, that's what I have said here, like similarly 2,000, 40,000. So yeah, coming to jet scores, this is a topic that's I think in chapter 5 itself. 5. Yep. So I have mixed the topics, like I didn't went in a way like first, fifth chapter, sixth chapter, seventh chapter, eighth chapter. I just did like a proper data science project, and I have included all these methods that are in our textbook. So coming to jet score, here we can see, like I have noted the points, like according there is a thumb rule, right? Like below -2 or above 2 are considered really possibility, like possible points. So based on that, I mean, I try to analyze the outliers because we don't want to waste any valuable data, right? So it's like, just if we think there are outliers, just dropping them blindly doesn't make any sense. We have to first analyze, and if we put in a probability way, we have to reject the null hypothesis that these are outliers, right? Then we can drop them. So that's what I did. And then coming to the next plot, I have drawn a box plot between sex and their medical expense if they are male, like their males and females charges. The median line, as I explained before, females have much more outliers. Like it has 25th, box plot, right? The first line is 25th percentile, the 50th percentile is the median line, and the 75th percentile is the end line. So like all in between itself, here itself, the 50% of the people are lying, and the rest 25% are here between 30,000 and 45,000, around 50,000. And males have less outliers, but the medical expenses of those outliers itself are very high. And coming to the same plot, it's just I have tried to do with smoking habits. The person with smoking habit has charges. What are the medical charges, right? So that's what is that. And the ninth plot is region, right? Because these are the categorical variables, and that's what I have to try to do. And yeah, coming to the 10th plot, I just want to know the relation between age and medical expenses, right? Like if a person's age is increasing, does that mean their medical expenses will slowly start to increase, or what, right? So this is what I have tried to do. So using this plot, I got to know that, like, while a person's age is increasing, there is a strong possibility that their medical expenses also tend to increase. It's clearly depicted here, and this is the same as like this box plot. I try to do in this plot, and using scatter plot again. I just try to see the distribution of body mass index, and here also, I mean, there is no clear line as it is in here, the blue line, but we can clearly see that as body mass index is increasing, the medical expenses are also slightly increasing, but it's not like so sure. Like there are many people in here whose body mass index is like from 20, 30, 40, but still their medical expenses are under 20,000, right? So it's not so clear, but there is clear pattern. When the body mass index is increasing, their medical expenses are also going to increase. Like there is a possibility. And this is one more interesting plot. I have taken reference from our textbook, where I can plot multiple data points instead of separate data points, so that I can analyze everything in a single graph. So it's an interesting plot. Like uh, it's basically between body mass index and charges. This is the same plot, but I have included a person with smoking habit and their sex as well. Circle is female and triangle is male. And here we can note a couple of things. All the people here, we said, right, there is not clear depiction. That's because all the blue dots, right, all the blue dots indicate they have a smoking habit. So we can clearly see, if a person has more body mass index, that means they are obese and they have a smoking habit. There is a strong correlation between them, that their medical expenses will definitely be high. You can see, if a person's body mass index, let's say, is 25, right? It's here, 25. 25 is very good. Like he's very healthy, right? I mean, he or she is in good shape. So 25, and he or she has a smoking habit, then their medical expenses is about 20,000. And if a person's body mass index is like, let's say 40 here, and they don't have a smoking habit, still their expenses is less than 10,000. So that indicates that more than body mass index, smoking habit is main reason for a person's higher medical expenses. And I just want to see what's how many males and females are there in the plot. And as you can see, uh, I mean, it's equally distributed. We can't clearly differentiate between male and female, but smoking habit does increase your medical expenses. And I just try to fit the density line just to see. Uh, I don't think I can zoom it, but you can see almost from the start to the end, males have more medical expenses than females, a little bit at least. And at the end, this sudden peak of the rise of female line is because there are many female outliers, right? As I said before, having outliers does shift your graph, does shift your results, uh, spoil your interpretation of the data, just because you have to include the outliers as well if they are present in your data. So you have to carefully understand the outliers, and if they are not that important and they're causing a shift in your results, you have to take care of them. That's what is happening. Like, just because of these few female outliers, the graph tend to increase suddenly to like almost 35,000, $40,000. And if let's say we have this portion of the graph and we think males have very less medical expenses, less than 20,000, and the females have more than 35,000. So that's not true, right? When we are taking the entire picture of the data, we can clearly see males have a little advantage, like a little more medical expenses than females. Yeah, this is the graph. I forgot. Like how. So the 14 graph is the just taking care of these lines in a clear line graph. So we can see from the start to end, males is the blue line, females is the red or orange line. It's clear that males have a slight advantage of more having more medical expenses. So these are the points that I have explained until now. So yeah, coming to statistical analysis, I think we are done with chapter 5, 6, and 7 visualization. So coming to chapter 8, which includes finding the confidence intervals, sampling the distribution, one-sided, two-sided, type 1, type 2 error, hypothesis stat. I think I covered almost all topics. So yeah, here I wrote them what I have included. I forgot. I think I have forgot to write the error calculations, but I have done that as well. Uh, yeah, just a second. I'm drinking water. Yeah. So let's check the yeah. So this is one sample. Like this is the t test, right? I have tried to check the BMI equal to 25 or not. Like I took a random guess. Let's say the average mean body mass index of all people might be 25, because 25 is obviously a good physique. So I just want to check whether it is a mean on average a person has that index or not. And we got the p. So we have to interpret based on this summary, right? And one way to do that is checking the p value. The p value is 2.2 e minus 16. That means very very small value, close to zero. So uh, what does that mean? Like, when we can figure out in a way, like if a p value is greater than 0.5, right? Like 5%, 0.05, sorry. So like if the p value is greater than 0.05, that means we can reject the null hypothesis. So here the hypothesis is assuming our body average mean body mass index is equal to 25. That's the hypothesis. So we have to check whether the p value is supporting that or not. So here it's clearly not supporting. That means we have to reject the null hypothesis stating mean is equal to 25. That means in original the mean is not equal to 25. Mean BMI is not equal to 25, right? So that's what the point here is. And Yeah, and again, I just did two one samples and then two-sided test, right? And one-sided, two-sided confidence interval test that I followed the textbook. And yeah, so using two-sided test, I have tried to do this T1 and T2. These are the T1 and T2. I think I have skipped them. Yeah, so the T1 is indicating that so here what I'm trying to do is mean body mass index of male and female. So the difference between the first one and second test is the first test is including the whole body mass index for the entire 1300 people is equal to 25 or not, right? The second test I'm going to do is two-sided test, which include two T scores. So the first one is mean body mass index of males, and the second one is mean body mass index of females. I just want to see whether, on average, a male and female have almost equal body mass index or not, right? So to see that so right now our null hypothesis is what? Like our null hypothesis is the mean body mass index of male and female are gonna be equal. Let's check with the p score. So the p value is around 0.08. That means, as I mentioned before, if the value is more than 0.05, that means null hypothesis is true and we fail to reject the null hypothesis. So we have to accept that they are almost equal, and that's what here is. Let's say that's what I have explained. So the third one that we are going to do is whether the average medical expense of the person is $25,000. So see, hypothesis is initially assuming something is true unless it is proven, like unless we rejected it, right? That's what the entire concept is. So the third test I'm going to do is the average medical charge of a person is going to be $25,000, as because as we saw before from the graph, most people have their expenses less than $25,000. So on average I want to see whether a person, if we take in a random, has a might have a medical expense close to 25. That's what entire statistical analysis is, right? We don't have to analyze the entire population. We just can take a small sample and analyze on that, and like amplify into the entire population the same thing. So I just want to see, and here we got the p value again. We have to reject the null hypothesis that on average a person has medical expenses is 25,000, because it's way less than 0.05. And the 98% confidence interval, I mean, it's by default 98. We can give whatever we want. I think I did later. So the fourth one, the fourth test I'm gonna do is yeah, average expense, the same thing. Like now I took instead of taking the expenses of as a whole, I want to check whether the male and female on average, if you take on random a male person and a female person and check their medical expenses, are they gonna be almost equal or different, right? So here we have to reject it. I think p value is less than 0.05, that's for sure, but it's almost close to 0.05. But if it's less than 0.05, we have to reject it. So they're not equal. The fifth question is, let's check the difference in BMI for every 1 year increase. Okay, yeah. So this is one thing I found from our textbook. Like I think they try to do similar analysis using different data. I think it's inbuilt R data, but yeah, I try to take that example as check, like if a person's age is increasing by 1 year, right? What's the increase in their medical expenses? That's a good point to check. Like let's say if a person until 30 years, every 1 year increase doesn't make a much change in their medical expenses, but after 30, if the expenses are increasing, we have to look at that, right? So here, this is called as paid t-test, because I'm comparing null hypothesis based on two values, right? So here the p-value is also again less than 2.2, like less than 0.05. That means we have to reject the null hypothesis. Sorry, we have to reject the null hypothesis that the difference in BMI and age is not constant, right? Like increase in age results in increase in BMI. That's what I want to say. Like because that's true, right? If we think on real life example, there might be a person with just 25 years old who is so much obese, their age is very less, but their BMI is too much high, and there might be another person whose age is 50 years and has a very good physique, so the BMI is in the scale like 25 around ish. So here the age is more, but the BMI is less. So that doesn't make a, a good hypothesis, and thus it rejected it. And the next one is, yeah, the next one is correlation test. I guess it's in chapter correlation. Yeah, it's in chapter 11, but I think I did here itself. Yeah, correlation. Sorry, where is, yeah, correlation in sense is like we have seven columns, right? And the seventh column is our dependent variable, which is medical expenses. We have to check whether if there is a correlation existed between a column which directly results in increase in medical expenses. So I did here a correlation between age and medical expenses because I just want to see whether increase in age results in medical expenses, increase in medical expenses or not, and the p-value is obviously less than the 0.05, thus we have to reject it. So as I mentioned before, increase in age doesn't necessarily increase your medical expenses. We got to know in this plot that increase in age is not the main reason. Increase if a person is having a smoking habit is the reason, right? Here. So yeah. So that's why here the the hypothesis is rejected, that increase in age doesn't make increase in your medical expenses. And the seventh question is, let's do the yeah. So ANOVA test is also in chapter, yeah, ANOVA test is in chapter 12. I included here itself. So ANOVA test is like it's helpful to test two well. Like it's like a two-sided test. Before we did two-sided test, right? Like checking the male average BMI and female average BMI. That's two different tests, and we are comparing the variance and mean of these two to check whether they are correlated or not. Like, so here using ANOVA test, I tried to check the relation between body mass index and age again. Increase in body mass index. So here it obviously have to reject it, right? Like before we already got to know here in this plot in the fifth question. Increase in age doesn't make a person increase in their body mass index. And here, while I'm doing ANOVA test, I got this. See, here I got to know that age is an important factor to increase in medical expenses, but that doesn't mean the body mass index is also going to increase. That can be known by the significant codes. If there are three codes like 3 stars at the end, that means it's an important factor that we will get to know in the machine learning part what the 3 star indicates. And then again I try to do the ANOVA test with body mass index and charges, medical expenses, right? Because before we said, if is increase in body mass index leads you to increase in medical expenses or not, right? And then the next one is yeah. So here I just, this part I'm confused to include where, because after linear regression I try to include this part, but I want to keep all ANOVA tests in a single place. So that's why I bought it here. So fitting the linear model with the medical expenses with all columns. The dot means include all things, right? Doing this, the ANOVA test included few columns, not all, because obviously it if all columns are included at the final model, it might lead to overfitting, right? That's again a part of bias variant. Instead of having all having all features means it's just leading to overfitting, and it doesn't necessarily make your model good. And having 3 stars, again I said, significantly important, right? So age is an important thing. What their gender is an important, body mass index, and children and smoker. These are the 5 columns out of 7 which are suggested by ANOVA test, right? Analysis of variance table. So variance table in sense is the difference of the dependency of all the columns with respect to the target variable, that is charges, medical expenses. Yeah, coming to machine learning part. So here I basically try to do two models, right? One is simple linear regression, and the second one is using cross validation, k-fold cross validation. I mean, I again use linear regression in that, but I try to do five-fold cross validation and again tenfold cross validation just to check the difference and is it improving anything? Just having more bulks of dividing in, because the thing is we need to have as much data as possible to get much accuracies, right? Having just 1,000 points doesn't make a model good, because the model to predict an unknown value like in test data, because the test data is not seen until it's given it's fed on it, right? So we need to have as much data as possible, like at least I don't know, but maybe more than 1,000 points to make a model first understand clearly. So there, like that's why I want to check with linear regression and cross validation. And here, as I said before, the carrot package that's used to this the data partition. I divided the data into 80%, 20%, and then uh, these are the basic things. The first one I created a partition. This is the reason I did that. I did not directly divide the data but use data partition is because it randomly chooses 20% of the data for test set and 80% of the data for train set. It doesn't make our data like the first 80% of the data, like from one first row to 800 row are going to training data, and the next 200 rows are going to test data. That's not good way of dividing, right? So we have to randomly pick 800 rows of 1,000 to train set and 200 rows on random to test set. That's what I use. That's what data partition I did. And then the target variable. I mean, from this, I have to exclude the target variable, right? From to future predict to compare the sorry to compare the accuracy. So here we can see the dimensions of the original data set that we have is 1,300 rows and 7 columns, and training data is divided of 1,000 rows and 7 columns, and 265 rows went to test data. Again, it's not the last 265 rows. It's on random some 265 rows. It might be first row and 10th row and like that, right? Then the first model is by default I gave all features, right? I gave all features and try to see, because here Anuva suggested us using ANOVA test, it suggested these 5 columns are important, right? Let's check what linear regression does. And ANOVA test did suggest us good or not. First, I try to give all and check the important features. And here again, interceptive will obviously be an important factor, and then age, it's true. And then body mass index, it gave children and smoke, right? And here it gave age. Here it said sex is an important factor, but linear regression said no, sex is not an important factor, right? And body mass index, yes, children, yes, smoker, yes. So again, from these five, again, linear regression rejected sex as an important factor, right? So now I try to fit the model again, but now I customized the model. I did not include the other four features which are not helpful, which are suggested by ANOVA and linear regression. So I just gave age, body mass index, and children, right? Sorry, children and smoke. So yeah, before going that, I just want to check the accuracies, right? So I just compared the original values and the predicted values by the model. And let's say the 15th person actual medical expenses is 39,000 and the predicted is around 31,500, right? It's not too good, it's not too bad, but it's close. And let's say 56th person, it's around the expenses are around 47,000 and the predicted is close to 40,000, right? So, and as I said before, I did error evaluations, and here I checked two, root mean square percentage error value RMSE, and the second one is R square test. And here, just to say what the values means is root mean square error value let us know how much overfitting our model is. If the value is more, it means our model is much overfitted, and if the value is close to, I mean, not close. There is no benchmark point of this much value is good, this much is bad. So that's the reason we have to check the r square test also. So r square test has a benchmark like close to 1, means the model is much good, right? Far from 1 means it has much more error rate. So it's around 76%, which is not bad. 76% of values are accurately predicted of, if like out of all 100 people, 76 people are correctly predicted. That's not bad, but as I said before, we don't have enough data points to accurately build a model which can predict very accurately, right? So so I customize the model, as I mentioned before, by the only features suggested by linear model and ANOVA. And let's check the uh, yeah. So here you can see they are the same points, but the predicted values are a little close, and the error rate is I mean, there is not much difference. It's just increased by 0.1%, but there is a difference. Because, as I said before, in of just 1,000 points, how many ways we divide itself, we need much more data. That's what I can say. But yeah, of the available data, that's not bad. And what is root mean square error value and r square, that's I already explained. That's what is here. And again, uh, the second one that I try to do is k-fold cross validation. First I tried with 5 folds, right? And using 5 folds of 1,000 samples, that's what it's saying here. uh, k-fold didn't make a model much good. Here r square, you can see it's 74%, right? It reduced it by almost 3%, from 77 to 74. And so these are the bunch of other error rates. I just before I just want every time generally check if it's you know continuous variable. I just check root mean square percentage error and r square test. If it's categorical, I just check confusion matrix. So here there are others as well. Okay, MAESD and MAE. Then the prediction values of the k-fold values. So you can see here it's much worse, right? The actual prediction is around sorry, the actual expenses of this 16th person is around $1,800, but the predicted value is $246. That's too different. And the 38th person is around 2,300, and the predicted value is just $362. So that's not good. But yeah, as I mentioned before, linear regression performed well, then Crayford cross validation. And now let's increase the folds. So basically increasing the folds, in sense in every sample we are going from 5 samples to 10 samples, right? So using 10 samples, let's check. uh, I don't think it improved a lot. So yeah, so the final conclusion is like the linear model did well than Crayford cross validation. And yeah, at the end I just want to plot, visualize, and conclude the analysis of which columns, like on real life, it also like it applies, right? What are the habits, what are the reasons that might cause our medical expenses to increase, right? The first one, all the models, like in both k-fold cross validation and linear regression, suggested is that if you have a smoking habit, smoker, yes, if you have a smoking habit, definitely your expenses are going to be increased. That is what like the importance in sense is, it's like 100%. It's very rare to have a feature which is 100% dependent on a variable, right? Like if it's like saying 100%, there is a 100% possibility that your medical expenses are going to be increased if you have a smoking habit. So then age, if you have if like obviously 20 years person doesn't have many medical expenses, right? He's healthy obviously. And if a person is like 60 or 70, they tend to have much more issues. And body mass index, that's the next one. And the children and region doesn't uh, have much importance. That's why they're like less than 10%, right? That doesn't need to be taken into account. But yeah, So at the end, these are my conclusions that I have like already said. So this concludes my presentation of the project medical expenses analysis. So James, Professor, thank you so much for the opportunity and looking forward to hear your feedback on it. Thank you.